Hello, everyone. Good afternoon, good morning, good evening. Welcome to the second keynote. So the second keynote speaker is Professor Jianzhong Li from Shenzhen Institute of Advanced Technology and Harbin Institute of Technology. Professor Jianzhong Li is a chair professor at Shenzhen Institute of Advanced Technology and a professor at Harbin Institute of Technology. He worked in University of California at Berkeley as a visiting scholar in 1985. And he was also a scientist in the Information Research Group in the Department of Computer Science at Lawrence Berkeley National Laboratory. He was also visiting professor at University of Minnesota. His research interests include big data computation and wireless sensor network. He has published more than 400 papers in top conferences and journals, such as Sigmod VRDB and VRDB Journal. And his paper has been cited more than 20,000 times, and the H index is 65. So he has already been many editor-in-chief in top journals in database. Next, let us welcome Professor Jianzhong Li to give us a keynote. Thank you.
So thanks for the introduction to me by Professor Li. Also, thanks for the organizers of the conference, giving me the chance to exchange idea about big data computing. So the title of my talk is Complexity Theory and Efficient Algorithms for Big Data Computing. So I will talk about 3 topics. The first one is the challenge of big data computing. So first, we should know what is the big data problem and what is the big data computing. Big data problem can be defined as follows. As input is the big data D and the problem P. And the output of the problem is a solution P on D. So the big data computing can be defined as the procedure of solving the big data problem. So now we can see the space of big data problems is very big and contains general fundamental problems, such as big data query, big data analysis, big data learning, and so on. It also contains application-oriented problems, such as industrial big data problem, medical big data problem, environmental big data problem. Here is some examples of big data problems. Okay, so first, let us see the process of big data computing. When big data problem is given, what we want to solve, how to solve it. First, we need to know, is the problem computable? If the answer is yes, the next question is, are there usable data? The usable data means they are data for the problem, and the data quality is very high enough for solving the problem. Then, yes, the next question is tractable. This means if the problem can be solved in desired time, yes, the final problem is how to compute it. So if we want to solve the big data problem, we need theory and algorithm of big data computing. So if we want to answer this question, we need computability theory of big data problems. To answer this question, we need theory and algorithms for big data usability. And if we want to answer this question, we need complexity theory of big data computing. Finally, to answer this question, we need efficient algorithms for solving big data problems. So traditional computability theory is enough for this question. But for these two questions, in these two aspects, big data computing faces many difficulties. Let's see. The difficult one is data is too big. Let us see. This is the examples, the big data. See, this data is 13 ZB per year, the 10 ZB per year, 283.5 EB per year, and so on. So this example tells us the data is too big to be processed by existing computers. Why? That's because the computing resource is limited. Let me see that. Everyone knows that computing resource now have a very big limitation. There are serious bottlenecks in I/O channel, communication and termination channel, and the I/O channel. For example, the general disk bandwidth is small, 1 GB per second, and SSD bandwidth is smaller than 5 GB per second. What happened? Let's see. Let's see the time for scanning big data one time. You see, if the data size is 500 PB, by this task, we need 15.8 years. By this SSDB, we need 3.2 years. For one EB data, this task need 31.6 years, and this one need 6.3 years. For this one, 6,000 years. We know that any accurate big data computing usually needs to read the input at least once. That means these are the lower bound of accurate big data computing. And this times is the linear function of the input set. Therefore, polynomial time is no longer the criterion of the tractability for big data problems. Also, some linear time has been the new standard of tractability for big data computing. So then we have the second difficulty. The limitation of computing resources makes the sublinear time become the time constraint of big data computing. So the two difficulties gave us two challenges. From the first difficulty, we have this challenge. That is, the traditional complexity theory has been shaken. And is no longer suitable for big data computing. The second difficulties tell us polynomial time algorithms are no longer capable of solving big data problems in desired time. So the two challenges tell us there are two research areas about big data. So area one is the complexity theory for big data computing. Area two is the efficient algorithm for big data computing. So now let's talk about what is the research problem of big data computing. But here, I cannot give all the problems. I only give the problems that we are working on. Okay. So the first research problem is studied computational complexity theory of big data problem space, the whole space, the complexity of the whole space. So the first, we need to study the computation model suitable for big data computing. So the new model should be accurately describe sublinear time computing process and support the analysis of time, space, I/O, and communication complexities. Also, we need to analyze the computational power and efficiency of the new model and analyze the equivalence between the new model and the traditional model. Second, we need to study the complexity structure of the big data space. Based on the complexities of time, space, I/O, and tractability, study the classification of the big data problems. Then, analyze the properties of the new classes, the relationship among the new classes, and the relationship between the new classes and the traditional classes. Finally, we need to study the new reduction to identify all kinds of complete problems. Then, we need to study the complexity theory of approximate big data computing. First, we need to build sublinear time L reductions to prove the sublinear time tractability and intractability of the big data problems. Second, we need to build sublinear time PCP theorem to prove the sublinear time intractability of the big data problems. Finally, we need to study the properties of the sublinear L reduction and the PCP theorem. Okay. We also need to study the complexity theory of parallel big data computing. So based on the complexities of time, communication, I/O, and the parallel tractability, study the classification of the big data problems, use new computation model. We also need to study the property of the new classes and the relationship among them. Also, we need to study the theory for analyzing the parallelizability, scalability, efficiency, and the speed up of the big data problem. Okay. The second research problem of big data computing is to study the computational complexity of big data problems. First, we need to study the inherent computational complexity of big data problems. Determine the lower bound of the time, space, and I/O complexities of the big data problems, and determine the sublinear time tractability and completeness of the big data problem. Then we need study the parallel computational complexity of big data problems, including study the lower bound of the parallel execution time, RT and P, the workload P times RT and P, and the speed up ratio is S and P, efficiency E and P equal to S and P divided by P, and scalability equal to SOEP, and so on. So we also need to study the parallelizability and the scalability of the big data problems. Okay, finally, we need to study the approximative complexity, computational complexity of big data problems. The many problems cannot be solved in sublinear time. So we have to consider the approximative computation. So first, we need to study the sublinear time approximability of the big data problems with and without arrow bound constraints. Then we need to study the minimum arrow bound for approximatively solving the big data problem in sublinear time. The third research problem is study efficient algorithm for solving big data problem. How to design the algorithm for the big data problems. First, we need to know how to design the exact sublinear time programs algorithms for solving the sublinear time tractable big data problems. And we also need to know design the sublinear time approximate algorithms for the big data problem that are approximable in sublinear time. Finally, we need to know how to design the instance optimal algorithms for average sublinear time tractable big problem. And we also need to know how to design the parameterized sublinear time algorithms for the big data problems that are parameterized sublinear time tractable. Okay, all the contents and the problems is in this paper we have published in 2016. So now I introduce some research work on big data computing by our group. So the first work is on computational model for big data computing. So as you know, the traditional Turing machine can hardly describe sublinear time computing due to its sequential access to its tape. So we need the mechanism to randomly to access the tape. So we call random access Turing machine. The idea is this. This is a traditional Turing machine. They have a tape key tape and a state. Now, for each tape, we add a binary write-only index tape. For each tape, add a index tape, and also add a new state, QA. So the difference is this. When RATM enters QA state, it will automatically move all the non-indexed tape to the positions that indicated by the index tape. So use this method, we implement the random access. So this is the formal definition of determinate RATM, denoted by a DRATM. So this definition is no big difference informal. So only have a new state QA and key index tape. So I don't want to say it. So we can similarly define the non-determinate RATM. It's the same, almost the same. When we denote the determinate RATM with the NRATM. So we have proved that the DRATM and the DTM are equivalent. If AS is a Boolean function and T is a time constructible function, then if T can be computed by a DTM in Tn time, then F can be computed by DRATM in Tn time. And if F can be computed by RATM in time Tn, then F can be computed by a DTM in time N times Tn times log Tn. So this theorem tells us two things. One is DRATM and DTM are polynomial time equivalent. The second is if F can be computed by a DRATM in time N power to 1 over K, then F can be computed by a DTM in time N power to 1 plus 1 over K times log N power to 1 over K. Also, we also consider the universal RATM. First, we see the determinate universal RATM. So this is the definition of the universal RATM. So DURATM is a DRATM with input XCM and output MX, where CM is the code of DRATM M, and MX is the output of M on X. We have proved that for any DRATM M, there exists a DURATM U with XCM as input and MX as output, which satisfy that U step in C T times log T steps on input X Cm if M stops in T steps on the input X, where C is a constant related to M. So we can similarly define the non-determinate URTM, also have the same conclusion. Okay, so this result is in this paper. The second work is on complexity structure of the big data problem space. The space. Okay. This year, first we are classifying the big data problem space. First, we divide into two subsets. One is NSL, one is non-NSL. So, what is NSL? P belongs to NSL. If and only if one, P can be solved by a sublinear time non-NRATM, and or after polynomial time pre-processing, P can be solved by a sublinear time NRATM. Okay, this part. How about this part? You can see that this part is the P include all the P that is not in NSL. Now we partition this part into two parts. See, the APPR NSL include all the problem that can be approximated in sublinear time by a NRATM. In APPR NSL include all the problem that not in APPR NSL. Then we can define a new class in the NSL. So the sublinear, actually the sublinear, what's meaning? The P belongs to SL if and only if when P can be solved by a sublinear time DRATM, or after polynomial time pre-processing, P can be solved by a sublinear time DRATM. Okay, this part we can give some also define a subset in this. So the APPR SL include all the problem that can be approximated in sublinear time by a DRATM. And in APPR SL include all the problem that cannot be approximated in sublinear time by any DRATM. Okay, we further divide this space. So this pseudo SL and this pro SL. What is the pro SL? The pro SL include all the problem that can be solved in sublinear time by a DRATM without any pre-processing. But this one include all the problem that can be solved in sublinear time by a DRATM with pre-processing. So we called pseudo. Then, so in this class, still have a special subset called PDP. What is PDP? So PDP is all the PDPC, the union of all the PDPC for C greater than 0. PDPC include all the problem that is computable by a DRATM in n power t times for C belong to 0 and 1. Okay. So we also have further, we can define the new class root. So root equal to all the equal to unit all the root k for k greater than 1 or equal to 1. The root k is include all the p. The p is computable by a DRATM in n power to 1 over k for integer k greater than or equal to 1. Then we have another subset. So this p log equal to the union all of PLOG power to C greater than or equal to 0, where p log power C include all the problem that can be solved by a log n C time DRATM for C greater than 0. Finally, we have the log time classes. So the polylog, poly-L equal to the union of all the poly-L-K. What is the poly-L-K? It is include all the problem that can be solved in log n power k time by DRATM for integer k greater than or equal to 0. So finally, the pseudo SL can be divided into 2 classes also. So for this one, P is in pre-SL if and only if there is a pre-processing procedure set such that 1 set D is greater or equal to D, and P set D equal to PD. Second, P set D can be solved by a DRATM in some linear time. But this one, so P it belongs to pre-RSL. RE. So see, for this one, the set D greater than that. For this one, the set D smaller than D. The other condition is the same. This meaning we can, for solving a big data problem, we can put more information, such as index, many structures. So make the data greater. This reduces the size. The idea is do more with less. We can, by sampling or compression, like that. Okay. Now, we have the roughly the structure, the completed structure of the big data problem space. Actually, we can do better. So we also find many new hierarchies. This is difficult to prove. So this is the result. Okay. So from the for each P equal 3R SL, how to make it sublinear time computable? We have three proposition. Proposition 1 is P set D equal to PD is computable in sublinear time if there is a C greater than 1 such that set D equal to D power to 1 over C. And P set D can be solved in set D power D times, where D is more than C. Then we also give another two conditions. Okay. For each problem in pre-Z SL, we also can give the condition. Under the condition, the problem can be solved in sublinear time. Okay, so this result you can find in these two papers. Okay, the third research work is inherent complexity of big data problem. Before, we just talked about the complexity of the space. Now, we consider the complexity of problem. So let's see. For analysis the complexity of big data problems, we developed two tools. One tool is SL, the sublinear reduction. We can see a function f is a sublinear reduction for reducing A to B if the following condition hold. One, for any x in sigma star, x is in A if and only if fx is in B, and f is computable in sublinear time. This is not a concrete reduction. So we have proposed several concrete reductions. So we give an example here. A is the subset of sigma. Sigma star is D log time reducible to B in gamma star. If there is a reduction function f such that x is in A, if and only if fx is in B, and this language belongs to D log time. Actually, this reduction, the complexity of the reduction is log n. So why we define the SL reduction? There are two usages of the SL reduction. One is to prove that A is computable in sublinear time by reducing A to B, well, B is computable in sublinear time. The second is to prove that A is incomputable in sublinear time by reducing A to B. Well, B is incomputable in sublinear time. Okay, we see the second tool. This we extended the traditional PCP theorem. PTP theorem is very important for approximative complexity. So we need we really need extended the theorem. So we need to define many things. So here, I think you may don't want to know it. So I skip it. So this is the PCP, the sublinear PCP theorem. Then the usage of the sublinear PCP theorem is to prove a problem is not approximate in sublinear time. Actually, to prove a problem is not approximate in sublinear time is very difficult. So use this theorem, we can prove many things. Then we can use the L reduction to further prove other problem that is not approximate in sublinear time. Okay. Now I give some example. The first example is the sublinear time computable problem. Let's say, this is the top K dominating set problem denoted by TKDS. Okay, we need a definition. Let T A1, A2, AM be a relation with n tables, and DC equal B1, BM that is belong to A1, A2, AM. So B the dominating criteria. So DC called the dominate criteria. For any T1, T2 belong to T, TE dominate T2, denoted by TE before T2. So if and only if T1, the value T1 on attribute BI greater or equal to T2 on attribute TI. For I greater than or equal to 1 or smaller than or equal to n. And there is a B belong to DC such that TEB greater than T2B. For any T in T, T's dominant score is defined as DOMT. So how many tables T dominate? This is the number. Okay. Then the problem is this. The TKDS problem can be defined as following. Input is R, A1, AM with n tables. DC is A1, AM, and K. The output is T such that the size of T equal to K, and DOM T1 greater than or equal to DOM T2 for all T1 belong to T, and all T1 belong to R minus T. Okay. So we see the sublinear time computability of TKDS is this. We prove that the TKDS problem is computable in sublinear time by using log n time preprocessing. That is, the problem is in pre-ESL. The proof is very simple. We designed the algorithm. The algorithm is satisfy these two conditions. One is as time complexity is n power to 1 minus 1 over m, sublinear. And we use three kinds of data structures. And the time to build the structures is n times log n. So this is the problem. This is a simplest problem. Now, let us to see some linear time approximable problem. That is not exactly computable, but it can be approximate. Okay. Example, we give the first example is evaluate data consistency problem denoted by EDC. Okay, we need some preliminaries. What is consistency? There is no conflict between the data and the object described by the data. We give a counter example. So see the table. Country code equal to 86. Area code equal to 10. The city equal to Shanghai. That is not correct. Why? Because 10 is the area code of Beijing, not Shanghai. So this is the consistency. Okay, how to represent data consistency? We use the conditional function dependencies. We see the grammar is d, x, y, t. The x, y is a function dependency, and t is a table of consistency constraint. We can see if t, we use an example to show the semantics. This is a CFD. So this means this attribute depends on CAC and the telephone number. So the table shows constraints. So the first table tells us if country code is 86, area code is 010, the city must be Beijing. If the country code is 86, AC area code is 451, the city must be Harbin. So the consistency of a data set D, the data model is consistency D equal D minus D mean divided by D, where D mean is the smallest inconsistent subset of D. Okay, now we can give the definition of the problem. The input is data set D, CFD set sigma. The output is the consistency D equal to this. So this is very difficult to compute. It makes the problem very difficult. See, so inherent complexity of the problem is like this. The problem is NP-complete. And even if sigma have only 2 rules and the data has only 3 attributes, the problem is still NP-complete. We have the corollary. So this EDC problem is not computable in sublinear time because it's NPM, because it is NP-complete. Okay. Then what is the approximability of the problem? 1, the problem is not 2 minus epsilon approximable in sublinear time, unless unit game guess is true. Also, if NP not equal to P, the problem is not 1.3606 approximable in sublinear time. And if sigma greater than 3 and D has more than 4 attributes, the problem is not 1.0625 approximable in sublinear time. So, but even this is very hard, but we can prove that the problem is 2 plus epsilon approximable in sublinear time. This is almost optimal. The 2 minus epsilon. There's a 2 plus epsilon. So we just designed the algorithm for EDC, then so that the theorem can be proved. So the algorithm satisfies 1 as time cost is log n, and as ratio bound is 2 plus epsilon, which is nearly optimal. Okay. This is also another approximable problem. This is a skyline problem. So in database area, we know this part. So I don't want to talk about it. Okay, again, to save time. Now, we come to the problem that sublinear time cannot be approximable. So this example 1 is a EXCK set problem. The definition of the problem is the input is a K-CNF formula phi. A is the assignment, is the set of assignment, alpha 1, alpha 2, alpha n, and alpha I equal to T, to K. Output, if there is an alpha star belong to A, satisfy phi, satisfy phi. If there is a alpha star satisfy phi, then return yes. Otherwise, return no. Okay. Let me see the approximability of the problem. We need a conjunction, the SETH. For any epsilon greater than 0, they exist K greater than or equal to 3, such that K set problem with n variables cannot be solved in 2 power to 1 minus epsilon times n. This is the conjunction. Now we can give the solution. So this problem is at least as hard as set. And this problem is approximate in sublinear time if SETS conjunction is true. We prove this theorem by tooling reduction. Then we use the SLPCP theorem, prove this problem is inapproximable problem. So this is the definition of the problem. The input is a set of bit vectors. V1, V2, Vn, bit vector and a bit vector with 0. The output is V star in V, satisfying V star times V0 is maximum. Okay. So the inherent complexity of the problem is this. Exact max inner product problem is not computable in sublinear time. Okay. Also, we have a theorem 4. The problem is not approximately computable in sublinear time if SETS is true. So cannot be computable in sublinear time. Also cannot be approximate in sublinear time. So okay. So this is the related paper. If you are interested, you can see them. Oh, so I have no time. So the fourth work is on design method of the algorithm for big data computing problem. So we have considered several investigated and proposed some new algorithm design method for big data problems. The first one is the compression computing method. This is big data, compressed data, computing on the compressed data without decompressing. This is the method. We have no time to consider it. Okay. So our solution is the compression method. The compression method is different from the general compression method. It must be support the computation without decompressing. Okay. This is the algorithm we developed for the compressed data. Okay, the second method is sampling-based Ypyong-Delt computation method. So we just look at it. And the third method is the dominant side-based computation method. Okay. Also, this incremental computation method, this is not our method, but we investigated, used we
是不是这样？是吧？
是
啊，刚才还有你那个讲到 ，OK， 你那个讲到你的 Scala， 我后来好像是那个就是溜了一下神 ，OK， 不知道是什么结果是？讲到 Scala 是那什么结果？有那什么结果
？So Scala is computable in sublinear time.
Okay.
So, but it's not belong to the pure SL. It's a pseudo SL. So need the actual data structure.
Yeah. 这和this is let me see. Yeah, actually also depends on the dimensionality, right? So when you have a high dimensionality, the problem probably is not.
Actually, Skyline algorithm has a linear algorithm to deal with it. So now we give a sublinear time algorithm with extra data structure.
Oh, you need to have data structure. Right? Yeah. Okay.
So that's not a per.
Okay, that's fine. The last question you also touched about the incremental computation, right? So is there any negative result about incremental computation?
What incremental?
Incremental.
Incremental computing. What?
You may know a negative result.
Negative, yeah. No. I have the positive result.
Okay.
All positive result. Because for the incremental computation, we don't need sublinear time. We just require that the complexity of the algorithm is the polynomial of the delta d, the increment, and PD, the result on d. Only that.
You may know a negative
because
result.
This is small, very small.
Yeah, very small. So
this two very small.
Okay, is there any negative result? Say, okay, for such a problem, it cannot be done, in delta. Okay, measured by delta, something like that.
Actually, I think we have some negative result. I'm working on now.
All right.
So I haven't find the positive result for the problem.
Okay.
We are trying to do that.
All right. Okay. Thank you very much. Very nice talk.
Okay, thank you.
Yiming, you can ask the last question.
Thank you. So, hi, Professor Lee. So, I'm Yiming Lin from a PhD student from UCI. So, I got two quick questions for you. So, first, it's about the definition of NSL and the pseudo SL problem. So, which both require processing time before problem computation, right? But this definition is kind of vague.
Slowly, I hardly can catch you. Yeah.
It's about the definition of NSL.
What is the first problem?
Pseudo NSL and the pseudo SL problem, which both require the processing time before the problem computation. So in this case, what if the polynomial processing capacity dominates the sublinear capacity of the problem computation itself? So how to define the boundary between the capacity between the pre-processing and the problem computing in this case? Hello?
Okay.
Is my question clear to you?
What's the dominate?
Yeah, so both NSL and the pseudo SL problem, they require pre-processing.
You mean the pseudo sublinear class include the problem that can be solved in sublinear time, but they need the actual data structure of pre-processing. So actually, the pre-processing can be done before the processing of the problem. For example, so in many cases, you can add some index on the original data set, then one time. Then later, you can use the index for many times. So this means the pseudo sublinear time. This is not the per sublinear time.
Okay, yeah, but my question is that what if because the pre-processing time using the structure you design is kind of polynomial in this case, right? So
but the pre-processing time is polynomial.
Yeah.
Because it's the processing maybe only one time.
Oh, okay. Yeah.
Just like index, you can do some processing.
Yeah, thank you.
Okay. So thank you, Professor Lee, again for the nice keynote speech. Thank you.